So hello and welcome to our last class that we're actually going to learn something new. This is Wednesday of week 15. This is the very end, and we are going to be talking about margin of error and the related subject of confidence intervals. In fact, if you look at the title of the section up here, confidence intervals, margin of error is actually in parentheses because confidence intervals, that's really the name of this thing, confidence intervals. Now, confidence intervals are extremely important. Between them and significance testing, and this is kind of like the idea of what statistics is all about. There's one fundamental difference, or I mean, there's many differences, but the biggest difference I think between significance testing and confidence intervals is that for significance testing, you have an idea of what a parameter is. I think P is this. Let me test it. And then based upon the results of your test, you either say, yeah, I think P really is that, or no, I don't think P is that. But you come in with this belief of what it is. With confidence intervals, you have no belief of what it is. You have no idea what it might be. And you're coming up with an interval of numbers from 10 to 20, from 25 to 30, whatever it is. You're coming up with an interval of numbers and you're saying, I have a certain amount of confidence that the thing that I'm looking for is somewhere in this interval. So this first example on the page, as a Rasmussen survey found that 59% of American adults say it is important for young people to go to summer camp. Now, the survey did not ask all American adults, it just asked 1,000. So this is what they reported. The margin of sampling error is plus or minus 3 percentage points with a 95% level of confidence. So what they're suggesting is, okay, the results of our survey were 59%. But that just comes from a sample. Is it really 59%? I don't know. But I can say this. I am 95% confident that the true value is between what two numbers? Remember, the value I got is 59%, but it's plus or minus 3%. So I'm 95% confident between where and where?
56 and 62.
56 and 62. You do 59% minus 3%, that gets you to the 56% on the bottom end. And then 59% plus 3%, that gets you to 62%. I am 95% confident that the true value is between 56% and 62%. That's a confidence interval. 95% confidence to be specific. If I had more confidence or less confidence, or my sample size was bigger or my sample size was smaller, then my plus or minus part would change and my confidence interval might grow or shrink depending on what I do. But we're not actually doing that here. We're just explaining what they did. And they came up with a 95% confidence interval and said that it's 59% plus or minus 3%. That is their confidence interval. The plus or minus 3%, the 3%, that's called the margin of error. How much error do we have? We have 3% this way, we have 3% this way. It's not a 6% margin of error, even though the total is 6%. The margin of error is how much you move in either direction. So it's 3% margin of error, 3% this way, 3% that way. So we have this concept of a confidence interval, and we have the concept of the margin of error, both of which are connected. Okay, so in this example, let's go through the various data points or the various numbers. N is the sample size. What is the sample size for this example that we just did?
1,000.
1,000, right? The survey did not ask all American adults, just 1,000. Okay, the sample size is 1,000. What is the proportion of yeses in the sample? The proportion of people who said yes or who, whatever it is that you're looking for, what is the proportion for this sample that we got?
Is that 59% of 1,000?
Well, the proportion is just 59%.
Okay.
That's the proportion. If I say, how many yeses are there in the sample? Then that would be 59% of 1,000, which is how much?
I'm going. I'm wrong. 59 times
590.
590. 590. Okay. The proportion of yeses is 590. Okay. Makes sense so far?
Mm-hmm.
What was
Okay.
our sample size again?
1,000. It says right here,
Okay.
right? It says
Right,
1,000.
right. Got it.
Okay. Now, what is P? The unknown population proportion that is being estimated. So in the case of significance testing, we always had the P, right? We always said, okay, you think P is this, let's check. Here we have no knowledge of P. So they're not asking for a number here. What they're saying is conceptually, what is it? What it is the true percentage of all Americans who think that young children should go to summer camp. It's a concept. It's the true percentage, whatever that is, which we don't know. We're coming up with an interval. We're saying, I think it's in here somewhere. Does that make sense?
Mm-hmm.
The
I'm
true-
just writing it
the
down.
true
So-
percentage of what?
The true
Again, please.
percentage of all Americans who think children should go to summer camp.
The proportion of all Americans who think children should go to summer camp, whatever that is, whatever that true proportion is, that's what P is. And we do not know what P is. Yes, Soler?
But we could say that P falls within plus or minus 3% margin of error.
Well, we can say with 95% confidence that P is somewhere between 56% and 62%. Is it definitely between those two numbers? I don't know. But I have a certain level of confidence that it is.
So we wouldn't say, we're saying the true percentage of all Americans, not 1,000 Americans.
No,
True
no,
proportion.
no. The thousands are sample. The thousands are sample. We're using the sample to infer something about the entire population. That's the goal. We're using our sample to infer something about the entire population. P is a parameter. It applies, about the entire population. That's what P is referring to. Okay, a parameter about the entire population. Chat question.
Sorry, I was just
Yeah,
confirming.
that's a true proportion of all Americans who think children should go to summer camp. And we do not know what it is. We do not know what it is, but we're finding an interval and we're saying I have a certain level of confidence that it's somewhere between this number and that number. That's what we're doing here. So in a survey about summer camp, each number between 56% to 62% is a plausible value for P. This is boxed, so you know it's important. Okay, this is boxed, so you know it's important. Each number between 56% and 62% is just as plausible as any other. Okay, so in other words, even though the number that we got is 59%, 59% is no more likely than any other number in that interval. And these numbers, these plausible numbers, make up a 95% confidence interval for P. I can do it in two ways. I can do it as it's 56% to 62%, or I can say it's 59% plus or minus 3%. It gets the same idea across. Does that make sense?
Yes.
So let's consider the following. Okay, let's look at it from another perspective. This perspective is a significance testing perspective, which we did last chapter. What we have here is a distribution created by using samples of size 1,000. Okay, this is samples of size 1,000. Why 1,000? Because it has to match our sample. Otherwise, how are you going to compare that? Our sample was 1,000, so these have to be 1,000. Otherwise, you can't compare different size samples. This one was created with the assumption that P is 0.7. This was created with the assumption that P is 0.7. How many successes did we have in our sample again?
The first sample was 590.
590. If P really was 0.7, how likely is it that we would get 590 as a result? Based upon this graph in front of us.
Not likely.
Not likely at all. In fact, it never happened.
Right.
Out of all the ones that came to this sample, it never happened not a single time. So if I was doing this from a significant testing perspective and someone said, I believe P is 0.7, you would say, well, if P was really 0.7, you're not getting 590 successes. Not with a sample of size 1,000. I don't see that happening. Does that make sense?
Mm-hmm.
Okay.
Can you explain how it looks on the graph?
Well, this is a graph that was made using samples of size 1,000, much like our sample, with the underlying belief that P was really 0.7. But we got a result. How do I do this? We got a result of 590, which is here, way off the graph. That's an extremely unlikely result if P is really 0.7. So unlikely that in all of our examples, it never happened, not even one time. So if I'm doing this from a significance testing perspective, my conclusion is P is not 0.7. Does that make sense?
Mm-hmm.
Okay. Now, this is another one where we still have samples of size 1,000 because that's the size of our sample.
Mm-hmm.
But this one has the underlying belief that P is 0.58. If P was 0.58, would 590 be plausible?
Yeah, because it falls between the margin of error.
Well, forget about margin of error. That's new stuff. That's new confidence interval stuff. I'm talking about significance testing stuff. Based upon this graph, if P was really 0.58, would 590 be a reasonable result?
Yes.
Tell me why.
Well, for one, 590 is now within our graph and everything in the bell curve.
Oh yeah, 590 appeared, right? This is 590 over here somewhere, this column.
Yeah.
That appeared over 20% of the time. That's a huge number of percentage of the time. Certainly it's plausible if it occurs that often, 1 in 5. Now, was 590 in our, was 0.59 in our confidence interval?
No,
For our, really? It wasn't?
I'm
I
confused.
thought we got
Pretty sure I'm
56
reading
to
this
62.
graph wrong.
Oh, confidence interval is the 56 to 62. So yes, it is. And
Yes, it is, because it's a plausible outcome.
got it.
70% is not plausible, so 70% is not in our confidence interval.
Okay.
Okay, our confidence interval is essentially the plausible outcomes. Does that make sense?
Yes.
Okay.
Me, I don't know about everyone else.
Well, the confidence interval, these are all the plausible outcomes. These are all the ones that are reasonable to be the value of P. 0.7 is not reasonable because 590 makes no sense. It would never happen. 0.58 is reasonable because 590 occurs quite often at 0.58. All of these percentages between 56 and 62 would have 590 be a plausible result. Anything past 56% or past 62%, 590 would just not happen often enough to make it plausible, and they're outside of our confidence interval. We'll do another example to illustrate this. So we did that, okay. Let's do the following. A study of 40 kleptomaniacs found that 14 had onset of the behavior of being a kleptomaniac before age 11. What behavior is that exactly?
I have no idea.
When you
Do you know
uncontrollably steal,
do you know what a kleptomaniac is?
uncontrollably stealing.
Uncontrollably stealing.
Ooh.
People who uncontrollably steal. I think a kleptomaniac is fun. I mean, horrible. Okay.
Nah, it's fun.
Thank you, Dad. So, what is the sample size in this example?
The 40.
40 kleptomaniacs. What is the proportion of yeses in the sample?
14.
No, 14 not a proportion. 14 is the actual number of yeses in the sample.
So it's 14 of 40.
14 of 40. What is 14 of 40?
14% of 40 is 5.6.
How much?
Hold on, let me do it again. 14% of
35.
5.6 is what I got.
14 over 40 was how much?
0.35.
Oh, okay.
35.
14 divided by 40. I was doing 0.14.
14 over 40 is 0.35, 35%.
0.35. There we go.
What is P? The unknown population proportion that is being estimated. Again, I'm not looking for a number here because I don't have a number for it. Conceptually, what is it?
Would that be 26 over 40?
No, it's not a number I just said. P is not a number. P is a concept. What is the price of alcohol? What are we, wait, what am I missing here? Let's take it a small, so there, I don't even know what to say. I don't even know what to say, other than me too. Okay, no, so P is a constant. What is P in this example? Someone tell me what P is conceptually referring to here. Not mathematically referring to, we had no number for it. Conceptually referring to.
Is that if you asked every single kleptomaniac in the world?
Nope. Yes, not asked, because we're not taking a survey.
So
It's
if
the
you
true value. It's the true value of what?
How
No
many
surveys here.
kleptomaniacs had the behavior before 11?
Yes, it's the true percentage of kleptomaniacs that had this type of behavior before age 11. We are trying to get a bead on this value. We are using our sample to do so. So P is just straight up the true value, whatever that true value is. We do not know what that true value is. In fact, we will never know what that true value is, because if we knew the true value, why am I taking a sample? Right? What's the point of the sample if I have the true value? Do you agree?
So just to clarify, it was the true value of kleptos that had this behavior before age 11?
Correct. It's the true value, whatever that true value is, that had this behavior before age 11. Now, next question. What is the 95% confidence interval for P? So here, we're going to figure it out. We're going to look at 12 different graphs. And we're going to use these 12 different graphs to decide what the confidence interval is. Now, what was the number of successes in our sample again? I forgot. What was the number of successes?
14?
14. We are only going to pick those P's that where 14 is plausible. And that's going to construct our confidence interval. We're going to pick the P's where 14 is plausible. So let's look at the first one where P is 0.1. Is 14 a plausible result in this one?
No.
Okay. How about 0.15? Is it a plausible result in that one?
Yeah.
Yeah.
14 is plausible?
No,
How-
no.
No.
It's still under 5%.
It's
Yeah.
think of it like this. The best way to think about it is think of your graph. You're only plausible if you're in the inner 95%. So if you're on the outer 5%, 2.5% this side and 2.5% this side, you're not plausible. So is 14 plausible for P equal 0.15?
No.
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 How about P equal 0.2?
Still not quite, maybe?
Well, maybe we're right around the edge of plausibility. So maybe a good starting point would be for our confidence interval would be 0.2. Maybe that's a good starting point for our confidence interval. What about 0.25? Is 14 plausible for 0.25?
Yeah.
Yes.
Yeah.
How about 0.3?
Yeah.
How about 0.35? How
Yeah.
about
Yes.
0.4?
There's several. Oh my God.
How about 0.45?
Yeah.
How about,
Yes.
how about 0.5?
0.5 or 0.45?
0.5.
I think we already did 0.45. We said no for that.
Okay.
No, it was plausible for this one.
Yeah.
How about for 0.5?
Maybe not.
Seems like now we're on the edge of plausibility on that end,
So
Where it ends.
right? So after
So-
0.5, it's certainly not plausible anymore. 0.55 is not plausible, right?
no.
Professor, I'm really confused on how to even read these graphs. So if I'm not mistaken, that you were saying that if it's under 5%, it's not plausible.
If your value of successes, which in our case was 14,
Right.
lies on the outside 5% of my graph, then we say it is not a plausible result. Okay, if you lie on the outside first of all, if you're not even appearing on the graph, you're certainly not plausible.
Right, I get that part, but like,
So like when I look at 0.5, for example, so 14 is right here. That's still plausible. That's not in the outside 5%.
what do you consider the outside 5%?
Well, I mean, you have to kind of look at the shape of the graph, and from the shape of the graph, I mean, we know we've dealt with the normal distribution, right?
Right. To see how I'm looking at that is I'm like looking at 14, then looking to the left.
Yeah.
Isn't that under 5%?
Well, I'm not talking about the height being 5%. I'm talking about the outside 5%, not the height of 5%, the outside 5%. Do you understand the difference what I'm trying to say here? Like
Not-
if you make a graph that looks like this, right? If I make a graph that looks like that,
Mm-hmm.
the outside 5% would be like the shaded portion there. Do you see it?
Okay.
Okay, it's 2.5% on the right and 2.5% on the left. Agreed?
Right.
So it's not a height of 5% that matters. It's whether or not you're on the right 2.5% or the left 2.5%. When I look at 14, which is right here, that is certainly not in the left or right 2.5%, correct?
Right.
When I look at this one, it's again not in the left or right 2.5%. When I get to here, now we're getting close to being in the left or right 2.5%, right?
Okay.
What about a 0.55? Is that in the left or right 2.5%?
Yes.
So at this point, it's already no question about it. So I would say like roughly 0.2 to 0.5 are the plausible p-values for which 14 successes is in the middle 95%. As such, that's going to be your confidence interval. Does that make sense?
Okay.
Yes? No? Maybe so?
Yes.
Yeah.
Okay. All right.
How
So
would we write out the confidence interval?
say again, what?
How would we write the confidence interval then?
You could say the confidence interval is from your confidence interval is from 0.2 to 0.5, exactly like I wrote it there.
Oh, okay.
Okay. Okay. So, okay. So this is, of course, not the way that we normally construct a confidence interval. We actually have a formula for it. Now, the formula is not given in the book, but I'm going to give it to you anyways, just because it'll be nice to kind of be able to compare what they get by their graphical approach to what we get. So the confidence interval formula is as follows. And I'm not going into why this is the confidence interval formula. You just got to trust me. It's p hat, which is your sample proportion, plus or minus 1.96 times the square roots of p hats 1 minus p hats over n. Do we know what n is?
Sample size?
The sample size. So p hat is our sample proportion, n is our sample size, and 1.96 basically comes from the fact that it's a 95% confidence interval. If it was a different level of confidence, I would use a different number. But this chapter never uses it. Excuse me. Sorry. This chapter never does anything but 95% confidence. And because it never does anything with 95% confidence, we're just always going to use 1.96. So let's do it for our example. The example that we just did, which was the p hat was 0.35.
Mm-hmm.
We get 0.35 plus or minus 1.96 times the square roots of 0.35, 0.65, because 1 minus 0.35 is 0.65, over 40, which was our sample size. So let's go ahead and run the numbers. What do we get when we do that?
I'm sorry, under the radical symbol, it says 0.35 and then parentheses, what is that?
0.65.
Okay.
It's 1 minus 0.35.
Okay.
So what do we get?
Hang on.
What do we get?
Times. I got 0.35 plus or minus 0.1478.
Okay, and if you do 0.35 minus that number and 0.35 plus that number, what are the endpoints of our confidence interval? 0.35 minus that number is going to be the left. 0.35 plus that number is going to be the right, plus or minus. So what do we get?
So we get 0.4978.
So about 0.5. Sorry, what do you get? You should get about 0.2.
0.4978 and 0.2022.
All right, so 0.2 to 0.5.
Okay.
Right, which is exactly what we got with the graphical approach.
Mm-hmm. Oh, right.
Right, we got 0.2 to 0.5. Okay.
Can that be written down really quick? I missed a few numbers.
So, oh yeah, go ahead. I mean, she's got it. She's so much better than I am.
Do you want me to write down like the whole process of the
Yes.
math? Okay.
Well, sure. You don't like mine? I have all the numbers here. What's wrong with these?
Just
Okay.
type that into a calculator.
Yeah, it's just 0.35 plus 1.96 times the square root of 0.35 times 0.65 over 40, and bam, out pops the answer.
I have that. I'm just the numbers, the answers.
No problem. Oh, so it's 0.2 to 0.5. That's what we get.
Oh, we rounded 0.49 to 0.5.
Yeah, just got close. You know, because that was the idea. It's about 0.2 to 0.5. So the graphical approach matches what we had. Okay, so I'm just going to wait for Tulare. I'm going to highlight her for a second. I hope she doesn't mind. And everyone, can you guys? Do I have to stop sharing for you guys to see her? Is she highlighted right now?
I see her. Yeah.
Okay, so I'll hold up a second.
Okay.
And there it is. What a lovely whiteboard.
Thank
so
you,
my
Tulare.
favorite.
It was kind of a waste. Anyways.
No,
Sorry?
I've been using it like every day,
No,
student.
not yours. Mine is kind of a waste. I don't use it. I mean, I bought it, and I don't really use it as often as I should. and I'll try to adapt next semester and try to be more more with that. But anyways, okay. To be honest, normally I don't teach from like the format of this course, which is the whole like here are the notes, use them. Is not how I normally teach. Usually I'm much more off the cuff, on the fly at the board. And it's just here like, oh, I use these notes. It's like, okay, I'll use these notes. All right, anyways. So
I
the
think
last
you can
Gallup poll.
spotlight me now.
Sorry, say it again. What happens?
I think you could take the spotlight off me now.
Oh, am I still?
I'm still spotlighted.
Hold on.
Pinned.
So.
Oh, I got it.
Remove spotlights. Okay.
Oh.
All right. So I'm gonna start sharing again. Okay, here we go. Okay. So the last Gallup poll before the 2012 presidential election predicted that Obama would get 49% of the vote. The poll of 2,700 likely voters gave a margin of error of 2%. Now, if there was a margin of error of 2%, what's the left bound and right bound of that interval?
$47 and $51.
47 and 51. Now he actually got 50.6% of the vote. Was that within the margin of error?
Yeah.
Yeah, 47 to 51 is right inside of it. The last Fox News poll before the 2016 election had a 95% confidence in the vote for the percentage of the vote that Trump would receive of 41.5% to 46.5%. What was the p-hat for that one? What was the p-hat for that one? What was it?
Do we have that information?
Well, we know that p-hat is directly in the center of the confidence interval because it's always plus or minus a given amount from the p-hat. So if I have the left bound and I have the right bound, how do I use those two to calculate the center, which is p-hat?
The average?
I average them. So what's the average of 41.5% and 46.5%?
It is. That's 5. So plus
4%?
5. So
I'm
4.
sorry, someone said it?
44%.
Yeah.
44%. Right? It's 2.5% from the left and 2.5% from the right. 44% right in the middle. That's the p-hat. And what was the margin of error?
Based on the middle, based on the p-hat we just calculated?
Based upon, yeah, the p-hat, the whole problem. I mean, I don't think you can do it with part of the problem. You got to use the whole problem. We have the left end, we have the right end, now we have the middle. So what's the margin of error?
2.5.
5%.
5%. It's how much you go from the center to either edge. Now we actually got 46.1% of the vote. Was that within the margin of error?
Yeah.
Yes, it was. Okay, so these predictions are actually not bad. Because remember, anything within the margin of error is as equally likely result as any other value. We don't just say it's the middle point. The whole confidence interval gives us the entire thing. Now, here's a formula for the margin of error. But this formula is not 100% accurate. And this formula that I already erased, but the formula that I gave above, that's 100% accurate. This is only an approximation, which is why if you actually look at the formula, what do they have between the E, which stands for the margin of error, and the 1 over the square root of n?
It's an estimate.
It's an estimate. It's an approximation sign. It's about. If you are estimating a population proportion P using the result p-hat from a random sample of size n, the margin of error E is approximately 1 over the square root of n. Let's see if this is true based upon the first survey that we did, which was the Rasmussen survey of 1,000 American adults. We got a value of 59% as a center, and we said plus or minus 3%, correct? That's what we said? You guys recall? Does the plus or minus 3% jive with what we have here? What's 1 over the square root of 1,000?
1 over.
What is 1 over the square root of 1,000?
It's about 0.03162.
It's about 3%.
Oh.
All right. So of course, if they're going to publish this article and it's a real, heavy duty article, they're not going to use an approximation. They're going to use the real thing. But it does show that our approximation is actually not half bad. Does that make sense? What about the one with the margin of error of size 40? What will be the margin of error for that one based upon our formula, approximately at least?
1 over rad 40?
1 over the square root of 40. And what is 1 over the square root of 40?
About 16%?
About, is that what it is? About 16%. About 16%. So what do you notice about the margin of error for the sample of size 1,000 compared to the margin of error for the sample of size 40? What do you notice?
Significantly smaller margin of error.
Significantly smaller margin of error. And of course, if you're going for maximum accuracy, then you're going to go for the smallest margin of error that you can find, right? So what is one way of getting a smaller margin of error?
Larger sample size.
A larger sample size, right? The larger the sample size, the more accurate it's going to be. Does that make sense and seem reasonable? I hope so. Now, what if I wanted a margin of error of 4%? What if I'm working backwards now? What if I say, I haven't actually taken my sample yet, but I want to end up with a margin of error of 4%. If I want to end up with a margin of error of 4%, what sample size would I need to accomplish that? What sample size would I need to accomplish? Oh, so look at that. So Lara already started. She said, okay, well, let's just go to the formula that we have. But this time, rather than plugging in the n or the denominator, which we don't know, we'll plug in the margin of error, which we do know, and then we'll do a little algebra. And what is that algebra? So the square root of x equals what?
1 over 0.4.
1 over 0.4. What is 1 over 0.4?
Which is 2.5.
2.5. And wait, just 2.5. 1 over 0.4 is 2.5? That doesn't make any sense.
1 divided by 0.4. 2.5. It's my calculator. And then you take the square root of that to get it.
0.4, Solaire. It's 0.04.
Oh, just kidding.
I'm like, that number is really, really small. That doesn't really seem like it.
Just kidding.
At all. So it's 0.05.
25. So 25.
No, so the square root of x is 25. And therefore, what is x going to be?
Rad 25, which is 5.
Whoa there, buddy.
Sorry, hold on. No.
Wow. Wow.
25 square root.
25 square root.
Isn't that?
You're squaring both sides, are you not?
Oh, I'm sorry. I'm tired.
How do you get rid of the square root side? By squaring both sides.
It's 25.
It's 625. So you can kind of like plan ahead and say, you know what? I don't really want a really big margin of error. I want a margin of error that'll be somewhat reasonable. Let's say, I don't know, 4%. And then say, okay, well, if I only want a margin of error of 4%, then I would need to have a sample of 625. So then you go out and you make a sample of 625, and then whatever you get, you know that your true value is going to have a margin of error of 4%. Does that make sense? Yes?
Yep.
Okay, now, This one's not really important. We're going to forget that one. Because that's not really that important. Not important, not important, not important. Let's do this one. A Harris poll conducted online with 2016 adult Americans found that 21% that said that they had some sort of tattoo. So let's fill in the values here. What's N? What is our sample size here?
2016.
2016. What is the proportion of yeses in our sample? What is the proportion of yeses in our sample?
21%.
21%. They gave us this information. What is the number of yeses in our sample?
21% of 2016, which is
Yeah, which is what?
423.36.
Well, you can't have a decimal as a number, correct? So what do we do with that?
Should we round it up?
Round it.
We round it to what?
423.
423. Okay, 423. What is P? What is P?
The unknown population proportion.
Of what? The unknown population proportion of what? Let's be specific. Of what? What exactly is it that we are measuring here?
How many of all American adults have some sort of tattoo?
That's right. The true proportion of adult Americans that have some sort of tattoo. It is a conceptual answer, not a mathematical answer, because we have no idea what it is. Now, C, what must be true before you can compute the margin of error? I think what they're asking here is a little deeper. Online polls are not the best polls to use, because who are the types of people who answer online polls? You ever answer an online poll?
No.
Okay, I will skip most of them. Which ones do I actually not skip?
The clickbait.
Well,
The ones on YouTube.
If you come across a poll and you can either do it or not, when do you usually do a poll?
The ones that you get paid for.
Okay, if you get paid for it, certainly. I certainly, when I come across a poll, even the ones that I don't get paid for, I really only do the ones that I actually care about. You know, like if I don't care about it, I'm like, I'm not going to waste my time. Who cares? You know, what do I care what the best Harry Potter book is? I mean, they all suck, you know? So it's like, we all have to decide, you know, which ones we're going to do. Now, the point that I'm trying to make is that an online survey is not a simple random sample. Okay, so if I'm going to use any of these formulas, I got to make sure that the survey that I use was actually a good representative a compilation of Americans. Like I can't go to like a website which is ilovetattoos.com and take a poll to see how many people have tattoos, because the people who go to that website are probably people who are more inclined to have them. Right? It's got to be an unbiased survey. Assuming it is, you can compute the margin of error. What is the margin of error, by the way? What is the margin of error?
How? Well, what must be true before we can compute it?
It has to be representative of the entire population.
Okay.
If it's not representative of the population, nothing we do makes any sense at all. It's a horrible confidence interval. Margin of error means nothing. Nothing means anything. If it's not a representative sample of Americans, then the whole thing is nonsense.
So now we're computing our margin.
So now we want to compute the margin of error. We have a formula for that. What is the margin of error in this case?
E equal or is about 1 over rad 2016.
Okay, which gives us what?
Hang on.
No problem. So what do we get?
Got
What-
0.022.
Yeah, so about 2.2%, give or take.
Mhm.
A fairly small margin of error. So whatever number I get, which is what, 21%, is between what, 19%? Well, actually, we can do it here. We are 95% confident, because remember, our formula is for 95% confidence, that if every American could have been asked, the percentage who would have said that they have a tattoo would fall someplace in the interval from what to what?
19 to 23%.
Approximately like 18.8 to 9 to 21, whatever, 23.3, whatever it is, right? Depends how much you want to round to. Does that make sense? Yes, no, maybe so?
Mhm.
Now, we can do confidence intervals for things besides proportions. We can do it for means as well. For example, the temperature of a random sample of 65 men was measured and the mean was 98.1 degrees Fahrenheit. A 98% confidence interval for the mean temperature of all men was constructed from the data, and they got 97.9 to 98.3. That was the confidence interval for men. A sample of 65 women, the same thing was done, and their confidence interval was 98.2 to 98.6. So first, is 98.6 degrees Fahrenheit a plausible value for the mean temperature of all men? No, it is outside of our confidence interval. Is 98.6 degrees Fahrenheit a plausible value for the mean temperature of all women?
Yes.
Well, it's borderline, right? It's on the very edge of our confidence interval, correct?
Mhm.
Right, borderline, let's say. What was the mean temperature of the women in the sample, by the way? What was the average temperature of the women in the sample?
98.2 plus 98.6 divided by 2, which is
8.4.
98.
8.4.
Oh, I didn't even have to calculate that.
Okay. Is this, well, yeah, you shouldn't have had to, but it's okay. Is this convincing evidence that women are hotter than men? Now, I want to specify that this question is referring to temperature and temperature alone, not any euphemistic variation of what hotter means. We all know the answer to this question. So from a temperature standpoint, is this convincing evidence that women are hotter than men?
Hmm.
Is this convincing evidence that women are hotter than men?
No, because they only asked 65 people.
Okay, so that's a very valid point. It's a relatively small sample. Let's say it was a bigger sample, but yet this was still the confidence intervals that we got. Would you say if it was 1,000 people, even though the margin of errors would be smaller, but let's ignore that for now. If you say if it was a huge sample and these were our confidence intervals, would you say that it's convincing evidence that women are hotter than men?
Yes, because the average is higher than the men's. The men's average is 98.1.
But if you're only going to talk about averages, then why even build confidence intervals in the first place?
I would look at the intervals, and between the both intervals, there's only 0.4 space between both of them.
Yeah, a little louder. It's hard for me to hear. Say it one more time.
So for the men, it's 97.9 to 98.3, which is only a 0.4 difference. And then 98.2, 98.6 is a 0.4 difference.
Okay, well, that's just because their sample sizes are the same, right? The sample sizes are the same. The margin of errors are going to be the same. So the size of the margin of errors isn't going to change. So what is it that allows us to answer this question? What is the deciding factor in deciding whether or not we have convincing evidence or just moderate evidence?
That the intervals is higher, like the interval of 98.6 is higher than the men's.
It is higher, but there's one aspect of it which is not higher. And that is that these two intervals overlap. There are actual numbers that appear in both intervals, and those numbers are plausible. What if 98.25 was the true value? Do both intervals contain 98.25?
No. Wait,
Really?
yes.
I'm pretty
Yes.
sure they do. That's why I kind of picked that number. So 98.25 is in both intervals. So because these two intervals overlap, we actually do not have convincing evidence that women are temperature-wise hotter than men. Okay?
So it's not convincing because they overlap?
Because they overlap. So there are plausible values that actually appear in both. Maybe men are 98.28 and women are 98.23, and really men are higher. Remember, we don't know which part of the interval is the right number. We just know any of those numbers are possible or plausible, better than possible. Any of those numbers are plausible. So because any of those numbers are plausible, 98.28 could be just as plausible as any other number. And as such, we can't conclude with convincing evidence that women are hotter temperature-wise than men. And this concludes Math 140. Okay, you have now learned everything that I desire to teach you. Not 140, Math.
I was
Sorry,
like,
140 is my 140 is my other stat class. What is this? 211 or something? Math
211.
Yay.
This concludes Math 211. You have now learned, or at least I have taught everything that I want to teach you. So we are now done. I'm going to stop recording our last lecture.